This video will show you how to set up a model that simulates matrix diffusion during transport in a fractured porous material. This is the geometry of the problem, and we'll assume that this is porous material, this block here, and then the line that you can see running through the center of it is a fracture. And for this implementation, if we zoom in here, we'll see that the fracture has some thickness. And so we'll treat the fracture as a 3D entity. It's got a broad planar extent, but it has some finite thickness that we'll include in the model. There's another way to implement a fracture where it has no thickness. It's just a surface in the model, but mathematically we give it some thickness or some aperture. But for this example, we'll assume the fracture has some thickness. So this is the model that I've set up, and I'll just walk through it and show you the important aspects. So we have a global parameter that's the porosity. This is the porosity of the matrix here, and we'll want to vary this and see what the effects of porosity are on the problem. So definitions, we don't have any. This is a pretty simple problem in that regard. The geometry, this geometry is going to be set up just as a series of rectangular blocks. There's this block, that's the entire block, and then the fracture is created using a thin rectangular block like so. And what we'll assume now is that there's flow along the axis of the fracture here, along the axis of the problem. The flow enters the fracture here and leaves here, and the flow is in one dimension. So to set that up, I used the transport of diluted species in porous media. So I included that physics, and that will bring along Darcy's law of physics to cover the flow, as well as multiphysics to couple these two physics together. Some previous models that I've set up for this problem use species transport in porous media, and in this file I've kept it in here but disabled it, but I've kept it in here for reference in case you have one of the older models you want to update. So I put in water as material, and then to set up the Darcy's law, this is going to set up the flow. So we've got some properties here, and there's the fluid is just from the material here, that'll be water, and then the porous material, we give it porosity, and we give it a permeability. This is a fairly low permeability, and this is the matrix, which is the material outside of the fracture. So the two big blocks here, and then with a separate matrix, fluid matrix properties, we define the properties of the fracture itself, and we give it a porosity and a higher permeability. The initial values, we just set the pressure to 0 initially, and we're going to have water coming in right here. That's the inlet, and we specify this velocity to e to the minus 6 meters per second. And then at the other end of the block, back here, we are specifying the hydraulic head, and we just fix it at 0. So pretty simple setup, and when we run that, we'll get a one-dimensional flow along the long axis of this rectangle. The other physics is transport of diluted species in porous media, and when we set this up, we want to include convection, mass transfer in porous media, as well as dispersion. And the setup here for the properties, well, here's porosity, so we need to include that, and we just use the same variable that we define as a global parameter to make the porosity definition consistent. And we give it a diffusion constant here. This is just the default. And the dispersion, I'm using the dispersion as this dl.u, that's the velocity, and I multiply by 0.1, so that would be a dispersivity of 0.1 meters. So this is just the default no flux along the outer boundaries, initial value concentration of 0, and then I'm going to have two concentration boundaries for the upstream entrance of in the fracture. In this one, I'm going to specify the concentration to be equal to 1, and in this one, I'm going to specify the concentration equal to 0. What I'm going to want to do for this simulation is run the simulation for a while where the concentration at the inlet of the fracture is equal to 1. That'll cause the concentration to spread during the transport down the fracture. And then I'm going to stop the inflow of concentration, inflow of mass. I'm going to set the concentration entering the fracture to 0. And I'll have then clean water flowing down the fracture, and there'll be diffusion back out of the matrix, and that'll be really the thing that we're interested in, that two-stage process of concentration entering for a while and then 0 concentration entering, and the concentration of the mass that's diffused into the matrix will then be diffusing back out. Okay, so I set up two boundaries, two boundary conditions, and then in the solver I'm going to set up which one to use. Under multiphysics, I have flow coupling, and I just need to make sure that the Darcy's law is used in the transport. So the mesh for this problem that I'm using looks like this. There's a triangular mesh up here along the top, and then I've swept that triangular mesh down through these three rectangular blocks. If we look at this side, you can see there's the triangular mesh. And the way to set this up is to first define the triangular mesh at the top, and then use these swept meshes, 3 of them, one for each of the rectangular blocks, to sweep it. And we define the distribution also in this way. So you can see how the mesh is more finely spaced as we approach the fracture, and this is because the concentration gradients will be steep right in here, so we want to have a fine mesh right in there, but it'll be much less steep out here, so we make the mesh spacing increase as we go away from the fracture. I have a separate video that talks about how to set this mesh up, so I won't go into really the details right now. So for the study, we've got 2 studies. We first run a steady state study here that is going to do the flow. So it's really set up just for Darcy's law, and it'll get the flow set up. So that's pretty straightforward. And then for this problem, we're going to use that steady state flow for the transport. So for the second study here, we've got a transient study, and it's going to use this fluid flow, and we're going to run the 2 different cases. Now, the way that I set this up, where we've got a time period initially where the concentration entering the fracture is equal to 1, and then we've got a second time period where it's equal to 0, I've set that up with these 2 study steps. So this one right here is set up to run over this range of time, and it goes from 10 to the 2 to 10 to the 7.3 with 50 steps. And then the setup for the physics looks like this. The setup here includes the transport, and what I've done is to gone in here, and this concentration boundary condition I've disabled. So let's see. When you first set it up, it might look like this with both of them lit, but then if you go here and press disable, it grays it out. So that means that this is the boundary condition that will be used, and it's right there. You can see the red, and this is the boundary condition that specifies the concentration equal to 1. So that's what we'll do for the first setup. We'll use the initial conditions just from the model, but see the values of variables not solved for, that's the flow, the hydraulic heads and the flows, and that's going to be from the steady state model here. Okay, so we've set up the first step like that. The second step also just uses transport. We've changed the time, so it starts from 10 to the 7.3 and goes to 10 to the 9. And in this case, the initial values of the variables are from study 3 transient time dependent, which is the sequence that we just ran, the step that we just ran. And it's this time. So essentially we're taking the last time step from this step and using as the initial conditions for the time step that we're just running. And we still use the same setup for the values of variables not solved for. Okay, so we're going to run, when we run this study, we'll run these two steps, and then when we get here to the end, we're going to combine them with concatenation. So this takes them, puts them together, and we specify the two solutions that we want to use. And what's going to happen is when you run this with step 1 and step 2, it's going to save it as study 3. You can see it's study 3, and then transient solution store 1. That's step 1, and solution store 2 is step 2. So with this node here, we're going to combine these two solutions and create one long result that has these two time sequences. We'll also be able to access each one of these time sequences individually in the data sets that are the results. Okay, so that's the setup for the study. And then when we go ahead and run this, let me show you the results. So here's solution 1. This is the steady state solution with the heads, and then we've got this is the concatenated result that has the two solutions together. This is the first solution and the second solution. I've got a cut point and a cut line. So the cut point is here. Now we've got flow going like this, and there's a monitoring point. And then I also have a line through there so we can get a profile. So what we see is that this is the concentration as a function of time, and we release the mass, and it takes a while to get transported along the fracture, and then this is what the mass looks like. It increases, and then we turn off the flow, or turn off the flow is continuing, but we turn off the mass. We set the concentration equal to 0, and then it falls, and it has this tail. So that's what it looks like if we plot it in log scale, and then this is what it looks like if we plot it in linear scale. Okay, so that's what we would see if we were monitoring the concentration. And here's what it looks like if we monitor the concentration profile. So this is the concentration profile at several times, and it starts out at 0, and then this is the profile here, this maroon curve, at fairly early times. You can see the concentration is moving out from the fracture, which is right here, and then this is the profile at a bit later time, but still the concentration is spreading. And then when we shut off the concentration entering the fracture, the concentration here decreases, and this is the next profile. And so you can see that we've reversed the concentration gradient. So now we've got diffusion back towards the fracture, and the maximum concentration is now here out in the matrix, away from the fracture. In fact, that'll occur throughout this period throughout that second stage. The concentration is decreasing in the fracture, but it remains higher out here in the matrix because there's diffusion. Well, and that would cause diffusion back towards the fracture. So here's the concentration, some slices to show you a bit of the 3D effect. And we can see the concentration spreading, and now the concentration is set to 0, and it goes, it's now 0 here in the fracture, and you can see this higher concentration zone out in the matrix. And this is what it looks like moving along the fracture. This is just the concentration along the outside. So it spreads along the fracture like that, and then it switches over, and we've got this clean zone within the fracture and these contaminants that are left out in the matrix. Okay, so I'm going to show you now a modification to the model that I just showed you that involved flow down a fracture. This has got a very similar geometry, except in this case we're going to treat the fracture as if it's a surface without any actual thickness. So if we zoom in here, we can see that the fracture this is the fracture, and in the previous model we had a finite thickness, but right now this is just a surface, just like the boundary of the model here is a surface. And you can see why that is if you look at how we set this up. Here's one block, and then we have a second block that we superimpose, and so this surface here that will be the fracture is really just the top of this second block. So the way we set this up, it's the same physics that we've used except in the previous example, except we go in here and in Darcy's law we use fracture flow and include that, and then we get a node that looks like this, and so we specify this surface in here as a fracture, and we specify the properties. So it has to have a porosity, a permeability, and an aperture. The aperture is the thickness, and so we'll call it 0.2 10 to the minus 2 meters squared for the permeability, and the aperture will be 1 millimeter. Okay, so that's the setup, and what we've done for this case is I just specify the hydraulic head on these two surfaces. So we impose a head gradient along this block, and let's see, we still go with the same properties that we had before, 10 to the minus 18. So this block is quite tight, except now we put this surface in here. And so what's being done is to take the governing equation for flow in porous media and apply that on the surface here, on this particular surface, as kind of a separate set of calculations, separate from what's calculated in the matrix. And that's what we're doing when we're using this fracture flow boundary. Now we do something similar for transport. We go and so we go to interior surfaces, and we use the fracture right here, and when we do that, we see it appears right there. And so we also select the region that we want to have as the fracture, and we give it some properties here, and the properties should match. So this one, we had it 1 millimeter before. This one is we would have 0.1 meters there, porosity, and we can change that to match. And now we need to have the diffusion constant and dispersion within the fracture. So we set this up based on the properties that we think represent the conditions that we want to simulate. Dispersion tensor, let's see, we used this for the dispersion. And let's see, then we have boundary conditions, and I'm going to specify the conditions on this surface here. And then the way I did this previously was to specify the two boundary conditions, one for specified concentration equals 1 and one for specified concentration equals 0, and we'll switch between them in the study. Okay, so that's how we set up the physics. For the study, we have a steady state study for the flow. This is set up same as the previous one, and the transient model, this also has these two steps for the different flow conditions. And let's see, let me show you how this works. We've got, if I check this box, I can get in here and alter the boundary conditions. So for step 1, I have this boundary condition is turned off, and then for step 2, I'm using the second boundary condition. I have the first one turned off. Okay, and then I also use this combined solutions at the end. Okay, so that's how to set this model up, where we don't we use the fracture as a surface. And the advantage of doing this is that we can avoid having to mesh a thin layer. Now, in the previous example, we showed how to mesh it with a swept mesh. That can be fairly efficient, but nevertheless, for some examples, we might have many fractures, and we simply wouldn't want to go ahead and mesh their thickness. It would add elements unnecessarily, perhaps, and complicate the problem. For some cases, we do need to have the fracture have a finite thickness. If we want the fracture to deform, for example, then it needs to have a finite thickness. But if all we want to do is have flow along the fracture, then we can do it this way.